again, our approach had typically been just apply more power, get more performance. Even if you were applying more incremental power to get that incremental performance, that was okay at small scale because power wasn't really a constraint. There wasn't a capacity constraint around power. It might impact your TCO, but if power is only 10, 20, 30% of your total cost of ownership, it's an operational expense that you're willing to trade off for more performance. But when power becomes the fundamental constraint to delivering capacity, the equation changes. And now you need to deliver additional performance per watt every generation. Just delivering more performance at lower performance per watt isn't acceptable.
The Compute 100 is a podcast about the most consequential market in AI.
These are the conversations with builders and investors about the technology and the capital powering the greatest infrastructure build-out ever.
I'm Brian Schechter.
I'm Gaby Lorenzi.
We're investors at Primary.
Let's dive into the Compute 100. This podcast is for informational purposes only and does not constitute investment advice or an offer to buy or sell any securities. Jeff Wittich, it's awesome to have you, Chief Product Officer of Ampere. Thanks so much for joining the podcast.
Thanks for having me.
We're super excited for the conversation.
Yeah, I'm too.
So let's start us off with where you're at today. Tell us a little bit more about Ampere, and we'll dive deeper into the CPU market more broadly, but bring us up to speed.
Yeah, so I've been at Ampere for about 7 years now. Ampere has been building high performance computing for data centers over the last 7 or 8 years. The key attribute that really sets us apart from other people is the focus on power efficiency. We long recognized that power was going to become one of the biggest constraints to building out additional compute. We saw that first in the cloud, and now we're seeing it pretty clearly in AI. So from day one, we set out to change the compute paradigm. We felt like it was possible to build high performance compute that was also power efficient, which might seem simple now, but typically power and performance are always kind of two sides of the coin. You can get more performance by consuming more power, or you can save power by reducing performance. But traditionally, you hadn't been able to both increase performance and reduce power. And it kind of required a different way of thinking about the problem and different way of architecting CPU. So it wasn't a trivial technical problem to go and solve, even if it seems relatively straightforward in terms of the value that it has for customers and for the market. So that's what we've been up to for the last 7 years. Again, focused on cloud compute first. As AI, especially AI inference, became a bigger piece of what was running in the cloud, that became a big area of focus for us. And then one of the really exciting things is that in late 2025, we were acquired by Softbank. And so now Ampere is running independently within Softbank and continuing to build what we've been building, but also working on some pretty cool, fun new stuff.
So I want to get to the sort of the SoftBank world domination strategy at some point, but maybe can you tell us like the origin story for Ampere and a bit about your background?
Yeah, so Ampere was founded in 2017. Renee James, who had been previously was president of Intel, she left Intel in 2016, wasn't leaving because she was done, was leaving because she felt there was another thing that needed to get built, and decided that building a company that was focused on power efficiency in high performance compute would have a good spot in the market. So she founded Ampere in 2017, quickly assembled a team of very experienced engineers, architects, technologists, largely from Intel at the beginning, but increasingly over time, pulling from a lot of other companies. And I joined Ampere in early 2019 when it was time to start building out a product roadmap and really looking at how we commercialized the things that we were looking at from a technology perspective, and how to turn this into a full business.
And had you spent time with Renee?
I had. We both worked together at Intel. Now, obviously, Renee had a pretty large scope of responsibility at Intel. She was running the fabs, manufacturing, software groups, a lot of other big elements of Intel. But we did work together at Intel. And so when it was time to add a product function and start to look at how the business side could be addressed from the Ampere perspective, she called, and I was still at Intel at the time. I was running the cloud business. At the time, it was an incredibly profitable part of the business. It had grown about 10x over the previous couple of years. But it was also evident that there were maybe some storms on the horizon, that things were changing in the cloud, that the problem statements were beginning to change. The scale at which the cloud was operating at demanded some different types of compute. And the more legacy types of compute that we were using at Intel to service that customer base maybe needed some additional technology investment. And so I kind of looked at whether it made more sense to push for those types of changes within Intel, big company where it's pretty hard to disrupt yourself from inside, or it made more sense to go somewhere else and really try and disrupt from the outside.
Yeah, I have an Intel question. So 2019, you've got this amazing growth in the cloud business. Mm-hmm. That's mainly selling CPUs?
It was mainly selling CPUs. That was certainly the bulk of the business, but it wasn't limited to just CPUs. We were selling other products in. So there was still a fairly healthy network business at the time, selling 10, 25, 40 gig NICs, even 1 gig NICs into cloud and data center. There was also the storage business. Mm-hmm. So we also had the NAND flash business. We were building other products as well. There were AI products at the time. This was after the acquisition of Nirvana. Mm-hmm. There was the Knights family of machine learning chips that Intel had developed. So there were a number of chips that went beyond just Xeon CPUs. We also had some memory products. This was around the same time as the data center persistent memory modules, the 3D, cross-point products. Mm-hmm. So it was really across the whole portfolio, although CPUs, did make up the lion's share of the revenue.
And you were overseeing all of that?
I was overseeing the whole product portfolio that went into the cloud. So we were looking at it, even though we weren't selling a system, we were looking at it from a systems level perspective. Yeah. The idea was to look at this as a system that was full of an Intel CPU, hopefully an Intel NIC with Intel storage products, Intel memory, maybe Intel accelerators, video accelerators, FPGAs, all these things working together in tandem to deliver the best possible result.
And so I'm really curious about because I think it's relevant to today where there's so much opportunity in the semiconductor industry. Mm-hmm. Of what is it like when you're sort of, you've spent your career in the industry, so we'll at some point kind of go back further. Yeah. But at that moment, you're seeing sort of foreboding signs in terms of Intel's ability to compete into a new world. What are the specific things that you're seeing happening, both in terms of the needs of the cloud and competitive dynamics?
Yeah, I think a couple things. One, the scale at which the customers were operating just far exceeded anything that we were used to previously. If you think about what the data center business looked like maybe 15, 20 years ago, you were selling dozens of CPUs into thousands and thousands of different enterprises. And maybe some enterprises were deploying hundreds, maybe 1,000. But even in those cases, it was deployments that were dispersed across a lot of different locations. You didn't have these warehouse scale data centers where there were tens of thousands or hundreds of thousands, and at a fleet level, millions and millions of machines. And so things that aren't evident and that seem like corner cases when you're selling somebody 50 machines are not corner cases anymore when you're selling somebody 500,000 or 5 million machines. And so it was starting to become evident that issues that were easily dismissed, things like silent data corruption, easily dismissed at small numbers, could not be easily dismissed at large scale. So not only did they become visible, they also had massive impacts because things like data corruption could end up cascading through entire fleets as data gets passed from machine to machine. And so it is a serious at-scale problem. I think the other thing is the power piece. Again, our approach had typically been just apply more power, get more performance. Even if you were applying more incremental power to get that incremental performance, that was okay at small scale because power wasn't really a constraint. There wasn't a capacity constraint around power. It might impact your TCO, but if power is only 10, 20, 30% of your total cost of ownership, it's an operational expense that you're willing to trade off for more performance. But when power becomes the fundamental constraint to delivering capacity, the equation changes. And now you need to deliver additional performance per watt every generation. Just delivering more performance at lower performance per watt isn't acceptable. And it became really clear to me as we worked with one big hyperscaler, we designed a whole product for them that did deliver more performance, significantly more performance, but it did so at lower performance per watt. So we're putting more additional power into the machine to get the additional performance. On paper, it looked great. It looked great from a total cost of ownership perspective. The problem is that when they spec'd out the entire rack, it became evident that a rack, which had a fixed amount of power, let's call it 14 kilowatts at the time, it was evident that once you spec'd this out into a 14 kilowatt rack, you were actually delivering less performance at the rack level than the previous generation. So for them to take advantage of it, that would have meant that they had to build more data centers to deploy more racks in order to take advantage of that additional performance, which was a cost that wasn't contemplated in the TCO equation and fundamentally showed that we were missing key constraints in our product design.
So I just want to know, who are the key players that sort of disrupted Intel at that moment around 2019? I mean, Ampere came in, but you guys were very successful, but didn't take over the entire world here. Like,
I think from a thought, from a thought perspective and a leadership perspective, I think Ampere did a very good job of coming in and disrupting and pointing out that power was in fact a major limiter. I think that overall the ARM ecosystem was a big disruptor here. You had people like AWS, eventually Google, Microsoft, that sort of took matters into their own hands and decided that if they couldn't get the products that they wanted from merchant silicon vendors in the x86 space, they could go and either design their own or have designed for them, their own CPUs that met their requirements in a more effective way. So I think that the overall ARM ecosystem was a big disruptor here. And then I'll say that AMD did an exceptional job of executing. Perhaps they were a follower in this, much like they followed Intel into the Xeon space with their EPYC processors, and they were able to out-execute Intel. They did a good job of also executing around power efficiency and taking advantage of the trends that were occurring. So I think that eventually AMD became a big disruptor to Intel, largely because they've executed extraordinarily well and delivered on time. And that allowed them to pull ahead. Maybe things that Intel felt that they could do or planned to do in 3 to 5 years, didn't happen. And AMD did a great job of making those things happen on time.
Power efficiency has turned out to be a great bet to have made in 2017, 2019 time. But I think honestly, a lot of folks don't truly understand what making a processor more power efficient looks like on a kind of technical level. So without getting too much into the weeds, talk through some of the kind of ways you can change the technology, the architecture. Power really stems from the place you generate it all the way it comes into the data center. But let's stay within the rack. Yeah. What are the key kind of levers that a company can pull on in order to make their hardware more power efficient?
Yeah, I think that fundamentally there's a couple of pieces of this. One is at the design and architecture level, just actually having a power first mindset is incredibly important. Again, it may seem simple, but in the past, power has always just been a trade-off that you could make to get more performance. And so building in architectural methodologies, building into your tools, power modeling very early on so that power wasn't an afterthought and something that you calculated after you'd already designed something, but it was actually one of the key inputs to how you made decisions about what architectural features go in, has been key. So again, it sounds trivial, but it means kind of overhauling the methodology and the tools, doing power modeling way earlier in the process.
And that's all software. These are before you even get to
hardware. Oh yeah, well before you even get to, and in fact, even before you even get to a design. Because as you go through this, we typically go through a fairly long pathfinding phase where everything's a bit theoretical. You're doing a lot of modeling, you're doing simulation, maybe you're starting to emulate some things. There's code snippets, there's kind of pseudo code floating around, but you haven't actually laid out any real circuits. You haven't actually created any of the blocks of the processor. A lot of this work has to get done then.
And that's happening in an EDA tool? Is this something that
potentially in an EDA
Cadence we're kind of helping support the industry,
potentially in an EDA tool, but also a lot of this is so early on that it's even pre-EDA. So it's actually we build a lot of our own performance and power modeling tools, building up suites of workload traces where you can go in and test architectural features in software before you ever even implement them in hardware. And again, a piece of it is not only being able to simulate or emulate the performance, but also the power consumption. The power consumption piece, if I go back 10 years, this was something that was done on sheets of paper, and it was Excel files, and it was just these back of the envelope calculations to see if you were kind of in the right power envelope. That doesn't cut it anymore. Performance wasn't like that 10 or 15 years ago. Performance was done very stringently. There was a very well-defined methodology around it. So a lot of it's just creating a stringent and repeatable methodology around how you do power modeling that early on. Because once you've made those decisions architecturally, they're really hard to undo 2 or 3 years later after you have real designs done, or even once you have silicon back, it's almost impossible now to go back in and redo those things.
And so it really was, if you, again, going back to 2017, power wasn't a constraint. And so even looking at and investing in power, like you said, simulation, design, and all of those things pre-hardware was I assume somewhat of a novel idea. And so what was kind of like the writing on the wall of, we need to look at power as something we bring, further upfront in our process? Was it largely just this idea of, this is how we need to compete? And by we, I mean like the larger industry kind of sentiment was that power was just going to continue to become more of an edge.
Yeah, I think it was twofold. One was looking at what the big hyperscalers were doing and having seen hands-on, where they were running into limitations. Now, I wouldn't say that even all of the hyperscalers totally acknowledged that this was the number one problem they had. There was always a bit of a disconnect where, when you look at the things that need to get planned from a capacity perspective for a data center, there tend to be a lot of silos. You have a group that's doing capacity planning and figuring out site locations and power capacity. And then at the extreme other end, you have a group of people that are focused on how to actually build and deploy servers that go into those data centers that were built years before. And there's a lot of other groups in between. I would say that going back 10 years, rarely did the site selection and the power capacity folks talk to the people who were actually architecting the servers that went into the data centers. So even 7-8 years ago, there wasn't consensus, depending on who you talk to within the hyperscalers, that the power capacity was going to be the big constraint. But I think if you talk to the people that needed to plan 5 years ahead, that were doing the data center planning, they recognize this as a problem. So I think we recognize that the problem they saw was looming on the horizon, and it was going to become everybody's problem. They were just the tip of the spear on seeing some of these things. So I think that was part of it. The second piece was just looking at the way that workloads were evolving and being in the CPU space and seeing how difficult it was to use existing methodologies to continue to achieve high power efficiency. It may not have been obvious to the outside world how much the improvements in performance per watt were slowing down. Like I could see this from within Intel, that year after year, we were having a harder time achieving higher power efficiency gen on gen. So that was a problem that was easy to see if you were internal to the problem, but hard to see if you were on the outside world. People often said, well, CPUs will just get more efficient. Don't worry about it. As someone who's actually building CPUs, you're the ones that actually have to worry about it.
You're seeing the power challenge coming with CPUs because of what's happening as the cloud is expanding its footprint intensely. Mm-hmm. The sort of news today is so much about GPUs, right, and how much power they require, and like the power shortage for the AI build out. But we're kind of coming back to a world where CPUs are becoming more and more important because of what's happening with agents and the complexity of the models and all the routing that needs to be happening.
Right.
How is that affecting the Ampere business today?
Yeah, so I think that it's just made our problem statement just more generally applicable. So yeah, you're right. Instead of just thinking about this in terms of CPUs need to become more power efficient because the cloud is ultimately dominated by limitations in power capacity, the problem got bigger in that it became an AI problem. So now that problem that, even if I go back 7-8 years, I was predicting that power demand for data centers could go up by 50% or 2x in the next decade. Well, we've blown past that with the AI build out. So I think the problem got bigger because now it's not just general purpose compute, it's AI compute, and the overall compute footprint just got a lot bigger. And then with the introduction of a lot of accelerators for AI, now it's an accelerator problem. And then the pendulum is swinging back to, and then now because there's a lot of other compute that goes into an AI system, CPUs are a problem in the AI space too. So I guess in that, like the whole problem just got orders of magnitude larger. So from an Ampere perspective, we have a bigger problem to solve. We're solving a problem around general purpose compute. We're solving a problem around AI compute. We're solving problems across multiple types of hardware, not just CPUs.
And is the rise of sort of the CPU as it pertains to AI workloads a sort of tailwind for Ampere right now?
It is certainly, the rise of more agent deployments. That has been a tailwind for us. I think that as you see a huge spectrum of model sizes and model types, some of them are really well suited for GPUs. Some of them are really well suited for specific types of accelerators. A lot of models run great on a CPU, and that is the more efficient way to run them. So I think the recognition that there's a wide spectrum of use cases and thus a wide spectrum of solutions for those use cases is certainly a tailwind. Because 3 years ago, it was all about GPUs running LLMs. Yeah. It was GPUs running multi-hundred billion parameter LLMs.
Part of our worldview is like that the volume of token output, AI-driven workloads is just getting so big that this multi-chip sort of workload-specific world that we're entering into with the Grok quasi-acquisitions, Rebus growing, more sort of ASICs coming into the world, and just more awareness of the role of the CPU. It's like, it's just, the volume is so big that the type of hardware that we need is becoming more heterogeneous.
That's right.
So that's one part of our worldview.
That's right.
Another thing that just kind of shift gears a little bit, because I want to hear about your experience of going from Intel to a startup, is that there are opportunities for startups to play in the semiconductor industry in a way that has been historically challenging. And there's one set of startups that are like kind of like the Ampere style of like, you got the dream team from Intel, it's very senior executive. We can get a lot of capital because of the experience.
Right.
We play at early stage investing where we're looking for, $5, $10, $15 million seed bets. I would just be curious, you've had one experience going, Intel into Ampere, which could make it feel like that's the only way to go. Do you have a point of view of the sort of the smaller, sort of earlier stage, less capital required startups? What is needed? I mean, I know you're a contributor to the startup ecosystem in general. Right. How do you think about where there are opportunities at the early stage and in that sort of broad landscape of so much fresh needs in compute?
Yeah, well, first of all, I'll say the cool thing is that there actually is an appetite for this today. Because when Ampere was starting, there was very little appetite for doing any early investment in hardware companies. Software companies, were attractive, but hardware companies, hardware it's expensive. There's large capital costs. It's kind of slow compared to software. At minimum, it's going to take a couple of years to design something, get silicon back, and then hope that it worked properly. So there's a pretty big risk associated with it, and it's hard to hedge some of that risk early on. So when Ampere was started, the idea of getting any kind of capital from VCs was impossible. We went the PE route because of the amount of capital required. Now, I will say that the scale at which Ampere was looking to build exceeded what a lot of other startups are thinking about doing. I mean, we had a pretty ambitious idea. It was taking on Intel in general purpose computing. So the most wide-ranging type of compute that you could build that required the most sophisticated, broadest ecosystem that you could imagine across OEMs and software vendors and open source projects. So what we chose to go into was a pretty large endeavor that was going to require massive scale really early on. And we also had some time constraints where you couldn't burn cash for a decade waiting to get something out. The cash burn is so high that you have to get something into market and scale it as fast as you possibly can because it's so resource intensive. There's obviously a lot of other models for a startup in the hardware space, especially with the rise of a huge spectrum of AI applications. There's room for lots and lots of pieces of hardware. They don't all need to be, multi-hundred billion transistor processors. They don't all have to have the scale of of a general purpose CPU. And so while we required a team of over 1,000 people to go and build something that was at a pretty large scale, there's an opportunity for startups that have dozens or a couple of hundred people that have a much lower capital requirement. And the good thing is there's an appetite now for investing in those, especially in the early stages. I think experience does matter. Now, I think that Ampere we were blessed to have dozens of people that had gone through 20, 30, 40 years of projects at an Intel or at a Qualcomm. So I think we had a wealth of experience and knowledge that maybe we won't see again. In this space, it was kind of a confluence of great timing with the industry changes and having the right people at the right place. I think having experience is useful. You don't necessarily have to have 50 people that have all had that experience, but I think you need to have at least a handful of experienced folks that have seen problems in silicon. Again, hardware, it's tough. It's a tough space, and there's a lot of lessons that you only learn through experience, and those are they are time-consuming and expensive problems if you haven't seen them before.
In that intention with that, there is, a rising generation of young founders and even just young operators who want to come enter this industry, are studying electrical engineering versus maybe traditional computer science. You studied electrical engineering. Tell us more about that.
Yeah, this is actually super interesting to me because I have spent a lot of time having a lot of conversations at universities over the last year or two. And it's interesting to see what's happened. So I was an electrical engineer. When I studied electrical engineering, I studied electrical engineering at University of Notre Dame as an undergrad. Typically at that time, you had to make a choice between electrical engineering or computer science, or computer engineering might be an option for some people. I loved computers. I knew that's what I wanted to do, but I also looked at electrical engineering as being a bit of a broader and more foundational discipline than computer science or computer engineering. So I figured that by studying electrical engineering and getting deep into certain elements, for me, it was solid state physics and semiconductor devices. By getting deep into that, it would give me the understanding of a core piece of this where the science isn't going to change. Obviously, we build on that science, but the core principles of how a transistor works or how semiconductors work, that hasn't changed in the last couple of decades. Whereas kind of the elements of computer architecture, computer science, like those will change over time because that's a discipline that's more a human construct versus a physics construct. So for me, I gravitated toward electrical engineering because I felt that was a great base for building a bunch of things on top of it. Now, over the last couple of decades, I will say electrical engineering hasn't been one of the more popular fields because it tends to draw from the same collection of folks who are also interested in computer science. Computer science and software development has been the hot thing for the last decade or more, especially things like the rise of robotics. People got really interested in the software side of it versus the hardware side. And so I had been helping a lot with recruitment for electrical engineering departments at various universities, trying to help them increase the number of students that were interested in hardware, because at Ampere, we're really dependent on having a great pipeline of electrical engineers coming in who can do great work for us. And it had been hard for the last couple of years. Some of the departments have less than half the number of enrollees that they had 20 years ago. I think interestingly enough, with what's happened in AI over the last year, you're now seeing a ton of people enroll in electrical engineering versus computer science, because I think that people are seeing how computer science is a field, because it's a bit more of a human construct, it's more of a field that AI can be readily applied to it, whereas electrical engineering is a lot broader and deeper. Like, it's the foundation for how a lot of things get built. And so you're actually seeing really high enrollment in electrical engineering, which I think is super exciting. It's really cool to see the number of people getting involved in hardware these days versus the last 10 or 20 years. So I think that there's hope for, if people are new enrollees in college or they're still trying to find their major. I mean, the fun thing is there's some awesome majors that are going to give you a front row seat to building a lot of this cool technology over the next couple of decades.
Yeah, and part of that, I think, is also college students. There's the sort of code gen, agentic coding. idea that being an engineer is no longer going to be a differentiator. That I think college students are quite stressed about.
I think that it's about looking at things a little bit differently. Like if you thought that you were going to college just to get trained to go write code and to go write a bunch of applications, like you might be looking at it a little bit the wrong way. You need to be looking at it in terms of your college experience is teaching you a way of thinking, a way of solving problems, like a foundational skill set for how you look at the world and how you look at systems and how systems come together. And so I think that this is maybe highlighting that if all you were doing was learning rote skills to sit down and code all day, maybe you were missing some elements of this. It's about problem solving, systems thinking, and there's still an amazing opportunity for people in that space. Again, maybe AI will replace a lot of the rote skills, or it'll be able to plow through a lot of simulations that require today a lot of hands-on time, iterating, changing parameters. But it isn't replacing people's ability to think about systems, solve key problems, invent completely new things, sort through ideas to find out which ones of them are good. There's an amazing opportunity for people who can think like that. And I think that's when you're looking at what people are learning in college, those are the types of skills that I think are most critically important.
Totally. It is really interesting, and it's great to hear that the pipeline of folks who are coming into this industry is growing, and we're seeing the same thing. Talk to me about what you would tell the person who's maybe like 5 or 10 years into their career, has been a software engineer, and is now seeing the thing that they trained for become commoditized and democratized in a way that's both incredibly exciting and also terrifying. And maybe they're saying, hey, I'd actually go rather work at a startup that's building in hardware. What are the kind of core functions and core skills that they can get exposure to that makes them an interesting candidate for someone like an Ampere or, the plethora of other AI hardware startups that are out here?
Yeah. Well, I think that, there's certainly a lot of great opportunities. I mean, maybe, for somebody who feels like their, day-to-day coding is getting replaced by AI, well, I'm sure that over the 5 or 10 years they've been doing this, they've learned a lot of lessons about what works, what doesn't work, kind of at a higher level, not on like a code debug level, but at a higher level, kind of how code interacts, how coding methodologies help to improve time to market. I mean, there's a lot of skills. So it's about, I think, thinking about things instead of thinking about it as lines of code written, thinking about it at the system level and kind of how is the code that you're writing fitting into a larger system, a larger product. And I think those are the skills that folks should be looking to take advantage of. And obviously in a startup, there's a great opportunity to take your experience. You have a lot of experience in knowing what works, what doesn't work, what breaks as you hand code off, as you merge code across teams. There's a lot of opportunities there to go and think about what is the system that needs to get built around this. Maybe you have a bunch of AI agents that are going and writing all the code, but somebody still needs to architect the system around all of this. Someone still needs to solve like the big foundational problems. So I think that there is a lot of opportunity, but it's not about just putting your head down and looking at the problem that you have to solve for the next hour. It's about putting your head up, looking around, seeing how you fit into the rest of the world, and using those skills to really fit into a bigger system.
What for you is a sort of early lesson that you kind of got at Notre Dame around this sort of first principles, whether it's systems thinking or how to think, that electrical engineering was so powerful. If you're talking to a potential someone's thinking about going into electrical engineering, and you want to like kind of give them a sort of snapshot into the type of thinking.
Yeah. Well, one thing that was really cool about the curriculum when I was at Notre Dame is there was a program that might have been the first or second year that they did it. It was called Bits to Chips. So the idea was, instead of looking at things as kind of individual subjects, you had some computer programming class over there, and maybe you had a solid state physics class over here, and then there was a circuits class over here. What if you actually thought about things holistically? Like if you thought about the fact that at the end of the day, what if you wanted to learn all the skills that would be required to actually build a computer chip? So think about it in terms of what's required to build a computer chip. You need to understand solid-state physics to know how transistors work, to know how you could fabricate transistors in a wafer and physically make the thing that you want to make. You need to understand how circuits work and how all these transistors interact with each other. You have to understand how to represent those circuits in code, so things like RTL. How do you actually design and code the products that you're going to make? And then what's all the software that has to run on this? You have to write operating systems and firmware and applications that run on the piece of hardware that you're building. And so this Bits of Chips program was kind of an integrated approach to thinking about how could you instill someone with all of those skills and then create a project that spans all those things. So we ended up building a chip where we designed it in RTL, we then laid it out, we sent it to be fabbed, we fabbed it ourselves in the fab, and then we wrote the software and the operating system. We sent it out, this was back in the days, this was probably like something insane, like a multi-100 nanometer fab. I can't remember now. There were a couple fabs for hire back at the time that were more oriented around like academic projects. So we sent it out to one of them. We fabbed it with them, and then we actually fabbed it internally as well in our own clean room to see how the result. I will say the ones that we sent out had a lot higher yield and worked a lot better. But we did have some working chips that we had actually fabbed ourselves. Where at least they were more or less functionally complete. So I think that kind of thinking where you thought about things not in terms of, I'm going to write a bunch of code and then there's this circuits class, but thinking about it in terms of how it all comes together into a product. I don't know if I really thought about it at the time, but that was great training for how do you become a product person? How do you ensure that you have deep knowledge in all these different areas, but also know how they all come together? And I think that as I look at my career, a lot of what I did was kind of early on move from deep knowledge in one of those areas to another one of those areas to see how those things all actually occurred in a in a real business setting until I had enough core knowledge around how this all happened, not just academically, but in enterprise, and then was able to go and own a whole product and then run a product roadmap.
And what are the skills required for that, like product ownership level at sort of at an Intel or what you're doing right now that you think has been benefiting you?
Well, I think that certainly, obviously, having great product management skills and interpersonal skills to be able to work across teams, certainly that's required. I mean, that's table stakes, and that is one of the hard things is that you're in a place where you don't necessarily own any of the work that's being done, but you have to integrate all the work that's being done by a lot of people, many of whom don't report to you. And so you don't have any kind of real authoritative leadership, but you have to use your influence and you have to use other leadership approaches to get a lot of people working together and want to make this thing succeed. So certainly that's a key skill set. But I also think that having deep knowledge of certain elements of what goes into the product, knowing how some of the teams perform their work, I think is really important because it gives you credibility with the team. That way you're not just the PM that's coming in and bugging people to get their deliverables done on time. You actually understand how they're solving their problems. It's not to say that you need to go in and do their work. You shouldn't go in and try and do that, but you at least have a perspective on what is the work that's being done. What are the constraints that people are probably facing so that you can help them solve their problems. And I think the last element is problem solving. I think that understanding how to formulate a problem statement, understand what problem you're trying to solve, understand what you don't know, what are the constraints to the problem, and then formulate possible solutions, I think is a big key to this, because just being the program manager that's just ticking boxes and bugging people because they're late, that's not really super helpful. That may satisfy the minimum requirements for the job, but the real value you bring is by being able to foresee risks, help people solve problems before they even pop up, help them get their heads up out of things and see how the work they're doing impacts other people, thinking about things from a system perspective. That's, I think, the real value that a program manager or a product manager brings to the table.
So acquisition closed in late 25.
Yep.
But I imagine this was coming for a while.
Mm-hmm.
what's it like? You're a couple quarters in.
Yeah.
Or not even.
Yeah, no, you're right. The deal got announced in March of 25. We went through the regulatory process. It closed on November 25th. So we're about a quarter in right now. So you're right. There's been a lot of time where we've been able to think about what it would look like, but not a lot of time where we've been able to actually do anything. I think that, when I look at the Softbank acquisition of Ampere, the key opportunities it provides us are, one, it allows Ampere to slot into a much bigger investment. The investments that Softbank is making in the AI space are massive, and they span a lot of different areas, from power to data center capacity to manufacturing. Working with big model builders, working in the physical AI space. We're able to slot into a much bigger opportunity than we were able to when we were just Ampere. With Ampere, we were able to build amazing products. We were able to work with great partners and great customers to get them into the hands of users. But we didn't have the opportunity to leverage multi-billion-dollar investments in different areas to go in and really shape the future of AI the way that we're able to within Softbank. So I think seeing how we can slot, kind of fit into a bigger investment profile, how we can work closely with some of the other groups within Softbank, like ARM, is also really critical. There's a lot of other great engineers within the Softbank group that are working on other cool projects. So it gives us a bigger set of projects to work on as well.
Quick, just sort of fact checked here. So with Ampere, were you using ARM-based IP?
We were. So we've always used the ARM ISA as the basis for our products. For those who aren't completely familiar with what the ISA is, it's the base instruction set. So it's kind of the really core instructions that you're able to get a processor to perform. And today, there's more or less two instruction sets that people choose between. There's x86, which is what Intel and AMD use, but that's a closed system. Intel owns the ISA, AMD licenses it from them, but there aren't any new licensees using x86. And then there's the ARM ISA, which is licensable. And so lots and lots of people, thousands of people use the ARM ISA because you can build a whole set of products based on that ISA because it's actually licensable. So we had been using the ARM ISA all the way from the beginning. And we also did use some ARM IPs as well. We built a lot of our own IPs. We used IPs from ARM. We used IPs from other third parties as well when there were IPs that are sort of commodity. There's not a lot of differentiation. So having something that just works is more important than having something that works differently than other people's. So we've long been working with ARM. So from that perspective, this has also been really logical.
And so spend a second just for folks who are unfamiliar with Softbank's portfolio. Softbank is doing an acquisition, has done a couple of acquisitions in this space. Tell us a little bit more about the players that they've acquired. And then, obviously this speaks to kind of the synergies among them, but would love to just, lay the context for who is actually in that portfolio.
Yeah. I think when you take a step back, the real vision that SoftBank and Masa has is around artificial superintelligence. So ASI as opposed to AI. The idea that it's not just being able to create machines that are able to think as well or nearly as well as humans, but the idea that we can actually create some superintelligence, which is really the game-changing piece of this. I mean, if all we've done with AI is replicate what humans can do and know better, there's some efficiency gains, but we haven't really changed the game a whole lot here. We have to find things that AI can do better or can only do that humans can't do. So that's the big vision is how to go and build out the platform for artificial superintelligence. But that platform is really large. As we talked before, power is a big piece of it. And so you have all these super integrated pieces of what it will take for an AI platform, an ASI platform to be successful. And that's having data center capacity. So there's investments in data center capacity. It's having power capacity. So there's investments in power generation and transmission. It's having models, foundational models, having the actual core AI technology built. So there's investments with companies on that front, like OpenAI. You need to have the actual foundational hardware. So there's investments.
Very big investments there.
Very big investments.
Softbank is like the biggest owner right now, right?
I believe they're yeah. I don't know if I can speak for the exact numbers, but it's very big. Yeah, we're talking about large, many billions of dollars investments. Many. Yeah, so you can see where the scale is a lot larger than the scale of.
They've double-digit ownership there.
Yes.
Yes.
But there's also hardware. So they acquired GraphCore a little bit more than a year and a half ago or so. And so there are other hardware elements. Obviously, the Ampere acquisition brings other hardware elements into it. So I think SoftBank and Masa are thinking pretty big about this. They're thinking about the ASI platform at about the biggest level you could think of. So the investments are all around how to go and create all of the competencies, how to create the capabilities in all of these different areas. And I haven't even mentioned, there's the physical AI space as well, where there's investments in manufacturing and robotics companies that I think will be the next frontier after we've gotten a steady state around how do you deploy compute in data centers to support all of these models. The next thing is going to be how do we embed AI in every device? And then it's going to be how do we embed AI in all of the physical devices and automobiles and factory robotics and maybe humanoid robots that can help us perform tasks in our everyday lives. I mean, there's a whole frontier there of things that do really start to get into that kind of like Jetsons.
One of the biggest surprises that the past few months for you?
Maybe it isn't a complete surprise, but just even the last couple of months, the pace of change within this space has increased. I mean, I think if I look back 3 years at the introduction of LLMs at scale, I mean, obviously not new in the sense that Google had transformers in 2017. It took a little bit of time before those ended up turning into LLMs for Gen AI. But the pace of change is fast there, and we've had new models. But I think that when you look at the pace of change across all these different use cases, and I maybe had an opportunity to stick my head up from the data center space a little bit and look around at all the other things going on in AI, I think that's been really eye-opening as someone who's always been really data center focused. Popping up and looking at, that's only the surface.
Yeah, that's cool.
Of this AI space.
I mean, so what comes to mind for me when you say that is, and this is probably sort of very VC centric, is what's going on with Claude in particular over the past few months. I mean, even us at Primary have seen our usage of Claude go from small to dominant. And our sort of AI usage as part of that also dramatically increasing. And it's the tangible feeling of like the model quality improvement is profound. What else? What are you seeing though? Because I feel like you're seeing so many different sort of disciplines in the context of the SoftBank universe. What's got you excited?
Yeah, I mean, I think that these days, I think that the physical AI space is actually super exciting. I think that if I look a year ago, I was probably a little bit dismissive of some of the initial use cases around physical AI because they seemed a bit, they seemed like toys. It was hard to see how exactly they could be applied to real solid use cases. But I think that when you look at the potential impact of physical AI in the world, we still have something like 1 million plus people a year still die in automobile accidents. There's still tens of thousands of people a year that die in factory accidents. There's still a large number of people that die in mining accidents every single year. So you think about places where AI can have a really substantial impact, could almost overnight, save 1 million plus lives a year. Physical AI is a really, really interesting space. And when you look at not the kind of toy applications of physical AI and what humanoid robots could do, but like the real game-changing applications, the life-changing things, you think of things like medical care or being able to, if you look at the way that drones could help with people. Again, like food delivery is cool, but think about actually delivering life-saving things to people via drones. I mean, there's a lot of really cool applications for physical AI. that go beyond what Gen AI, the stuff we have been playing with a lot the last couple of years, like what it's capable of.
And what are some things that you've seen that are making you say like, oh wow, this is coming?
When you look at the improvements in the mechanical robots over the last couple of years, I mean, it's staggering when you look at what a mechanical device can do today versus what it could do 5 years ago. So I think that if there was a fear that we were limited in what like the terrain a robot could cross or how versatile a robot could be, like those seem to be kind of out the window at this point. And so now that opens the door to go and apply compute to these problems. And so I think that I think it's unbelievable. I mean, honestly, we see it every day and maybe it's become a little bit commonplace, but you know, when you look at autonomous driving, I don't know I think we underestimate how impressive this actually is.
If you live in New York and visit San Francisco, it's every time it's still a delight.
I know, and I feel like I get so used to it here. But I mean, even driving here this morning, you look around and there's a Waymo to the left of you, to the right of you, ahead of you, behind you, and you don't even think twice about the fact that there's nobody driving these vehicles. That most of the cars around you on some blocks are all autonomous. And so it's easy to highlight the small number of cases where things don't go well, but it's dwarfed by like the million times more cases where everything goes so much better than it would with a human driver. So I'm really excited about that. Like I think this is where like the next frontier is for AI. And I think that while again there'll be weird use cases that are easy to dismiss in the space, there's also clearly massive use cases where these types of devices will be able to do things that humans just physically cannot do, or that humans should not be doing physically because they're just too dangerous, which I think is just, again, Gen AI has been amazing. It's been a great productivity tool. It's allowing people to be a lot more productive, get things done faster. But physical AI is this place where I think will actually be able to do things that you just cannot do with humans alone.
Mm-hmm.
Let's maybe draw a quick connection to the CPU business and market
that's great.
and its role in the physical AI future. I mean, if you think about, there's one world in which autonomous vehicles end up becoming a distributed fleet of compute, and that's maybe the Elon future.
Yeah, maybe so. CPUs, anything compute related as it pertains to physical AI, like what is, and we're curious about like, well, what types of startup opportunities should we be looking for? Saying like, oh wow, this founder is like seeing the future with physical AI, and they have this very specific insight about compute that's needed.
Yeah, I think that when you look at physical AI, just like I think that data centers will look really heterogeneous. I mean, physical AI is a space where you're going to have a lot of heterogeneous solutions. In part because the use cases are a lot more varied. Data centers do have varied use cases from a software perspective, but at the end of the day, it's a bunch of machines sitting in a warehouse. Once you get out into the physical AI world, now it's a bunch of compute that's embedded in thousands, tens of thousands of different form factors that all have different environmental conditions. So the solutions will be incredibly varied. I think we will see everything from big distributed compute systems where everything is communicating to super isolated systems that maybe only phone home every once in a while and have to be pretty autonomous, to systems that always have to phone home and are connected to some massive data center behind the scenes that's performing all of the compute. So I think that it opens up a pretty wide set of problems to go and solve. I think the easy ones to identify are, there's extreme space and weight and power constraints when it comes to a lot of the physical AI use cases. So any solutions that allow us to pack more compute into a smaller area consuming less power are going to be useful. Given the fact that there will be a lot more either distributed or isolated systems, but clearly not massively centralized systems, it also opens up the opportunity to solve some big technology problems, not just in how much compute to pack in, but how do you access enough data quickly enough in these types of systems. So data access, memory, storage, these are going to become really big constraints. From a networking perspective, it's a different networking problem. You've got wireless connectivity is potentially a big piece of this. You may also see some systems where optical maybe becomes more desirable in these systems faster than in data center. So the movement from copper to optical could happen in some of these systems a little bit more quickly because copper, is a bit constraining, not big reach. It can be, it can be a bit space intensive when you look at the number of cables that are required. So I think, I think it opens up the door to solve a lot of the almost solved problems that exist in the data center space. These become bigger, in some ways, more constrained problems, but problems that have more unbounded solutions, I suppose, that can take more flexible types of solutions in the physical AI world. There's just a lot of creativity, tons of form factors. And I think that the great thing in this space too is that, if this were a baseball game, I don't know what inning we're in the data center space, but we're somewhere in like the first couple innings. But the game has started. We're in the game. I think when it comes to the physical AI world, we might be first pitch. There's a ton of opportunity to define this because it's a pretty undefined space right now. And so I think that's fun from a startup perspective. You're not necessarily trying to slot into an existing solution to go and unseat an incumbent that has a really well-established solution that you have to, where you can't change all the variables because a lot of the variables have already been defined and locked in. This is a space where virtually none of the parameters are locked in and defined. So that's a fun space for startups to be in.
We're excited for the rest of the baseball game. So
for sure.
It was awesome talking to you, Jeff. Thank you so much for joining us.
Yeah, thank you for having me. This is great. Lots of fun.
Awesome. Thanks.